So I want to thank Luke for inviting me to give this talk, and for putting me on the spot to putting something up together on a topic that I don't work full-time on. So I'm going to talk about reconstructing past ocean circulation using benthic and planktonic foraminifera. And so I should have mentioned that Luke and Emma Freeman are my collaborators on this. And so the way this works is they collect in sediment cores foraminifera, some in the sediments through time in the past, and some of them record the radiocarbon at the surface of the ocean, and some of it recorded at the bottom of the ocean where they live, but then they get buried together in the sediments, and you can pick apart the different forams and learn something about the gradient in age in the seawater. So they both record, there's two kind of signals recorded in them. One is how old the sediments are, and the other one is the age of the water they were living in. And for the purpose of circulation, we need the age of the water they're living in. So for the purpose of this, this inversion, I'm going to use only the difference between the surface and the deep radiocarbon ages. But some of the cores are so well dated that there might be actually 2 bits of information relevant to ocean circulation. But so far I have not used these. All right. So it's kind of an interpolation problem that we have. We have these records of water mass age from the foraminifera. And now the question is, how do we extrapolate these sediment core measurements? So they're very few, they're very sparse, and we'd like to say something relevant about the global ocean. And if you think about one point, then it's influenced both by water upstream, so it has information about the different water parcels that have mixed upstream into this region. So you might think, well, the foram is telling us something about upstream, some zone of influence of the age of the water. But conversely, you might think, well, if we know the age of the water at this point, then the downstream is going to be influenced by what you've recorded at this point also. And it becomes kind of hard to try to use circulation information to do the interpolation. That's the kind of the problem we had. So after scratching my head for a while, we've come up with this, the approach I'm going to show in a little bit, which is basically trying to assimilate radiocarbon data in the model, but so far we're doing it in a very unconventional way. So the simple model I'm going to use to do this is a very coarse resolution global ocean circulation model. It's about 4 by 4 degrees resolution and 29 levels in the vertical. And it's a linear parametrization of the radiocarbon equations. So if you were just trying to go from scratch and try to estimate the advection diffusion operator from your radiocarbon measurements, it seems kind of hopeless, because even in a very coarse model like this, there's about 10 to the 6 million non-zero entries in the advection diffusion matrix. And maybe we have on the order of 100 or so radiocarbon measurements to try to do the inversion. So obviously, we're going to have to build some prior information into what's possible in terms of ocean circulation. You can't just go blindly and hope that a few measurements will tell us everything about the circulation. All right, so what I've done is taken this equation for the advection diffusion of radiocarbon, and I've broken up the transport into this superposition of tracer transport operators. So how did I get these? I ran a whole bunch of general circulation models with different surface forcings, different mixings, essentially different mixing and different subgrid scale parametrization, and let them run out to equilibrium dynamically. And then I reconstructed the annual average advection diffusion tracer transport. And now I'm just going to take a linear combination of these advection diffusion operators with some weights out in front, these e to the alphas here. And I'm going to try to use the radiocarbon data to fit these weights. Now, if there's any dynamicists in the room, they might put up their hand and object right away. They're going to say, you can't just average the transport from a bunch of different simulations because it's a nonlinear process. So that's true. But I'm just going to view this from a kind of a kinematic point of view, that we want a properly formed advection diffusion operator that can move the water masses around in a sensible way, so without kind of having water appear and reappear. So it has to be conservative. And it has to have continuous pathways. So this method of reconstructing kind of does that. And I was kind of fortified to do this by Jake Deby's work, where he's shown that you can kind of reconstruct a sensible transport operator using only tracer information and throwing away any dynamical information. So I'll blame him if you're still dissatisfied with this. All right, so you'll notice that all the little weights in front are put into these exponents, so I use a logarithm, and that's to make sure that all my weights in the end are all going to be positive, because if you get a negative one, that's essentially negative diffusivities, and that's not allow your model will blow up in an instant. So that way I'm sure that all my combinations are going to be well posed. I've also included one more here for the rescaling the air-sea gas exchange. And this is the only one that's kind of, you have to be a little bit careful, because at least in some cases, if you let this to be totally free, then you can get some crazy reconstructions. All right, so what we've done basically is parameterize the circulation, a three-dimensional field with a handful of parameters. In the results I'll show you, I have only 12 of these weights, so it's a small group of parameters, less than the number of radiocarbon measurements we have. All right, then this is just to tell you where I got these advection diffusion transport operators from a paper written by Tim DeVries and myself in JBC. And I'm not going to go through what they all are, but they have different salinity and wind forcings and different mixing rates. And they were easily available, so I've been using these. All right. And then what we do is we just write a Bayesian approach, the probability of the data given the model. And this is just given as some Gaussian normal distribution for the difference between what my model will predict given these alphas and what the data gives us. And and this is done in the radiocarbon age. And what we're doing is that the data is remember, it's the benthic planktonic difference. So it's the difference between the surface and the deep. All right. So I'm going to test this in two situations. Well, one's a test, the other one is a preliminary application. The results are very preliminary. So the real application is going to use some actual radiocarbon data. But the first test, what I've done is I've applied the method to a GCM radiocarbon simulation. So the model that I have for my tracer transport operator is a very different model than the one I'm going to do for the test, just so you know that it's not too rigged in advance so that it'll work. So the GCM that produced my pseudo or my fake LGM data is a state-of-the-art climate model. So it's a 1 × 1 degree resolution model. It's the CESM climate model. And there aren't very many radiocarbon simulations at that resolution. And there's a paper by Barden and myself and Keith Lindsay where we've developed some fast ways of spinning up ocean tracers, and that allows us to do one of the first radiocarbon simulations at that resolution. And what was maybe, I don't know how surprising it was, but the point is that even if you know the surface forcings very well and you have the state-of-the-art parametrizations, you're not guaranteed to produce a reasonable radiocarbon measurements, which tells us radiocarbon is a very useful tracer for learning about ocean circulation. Because before when they never simulated the radiocarbon, they perhaps weren't as aware of these huge biases in the model. So I'll show you the results in a little bit. But the point is that I'm going to use this model as a fake LGM data to test the method. The transport operators are based on a model that maybe was state-of-the-art in the 1990s, whereas this one is the current CESM model. All right. So this is this CESM pop. So it's meant to be a modern circulation, but I'm going to take it as an LGM circulation simply because it's very different than the modern. So this is actually what modern observations would tell you what the age of the water. So this is a zonal average in the Pacific. And you could see that in the modern observations, the age is maybe on the order of 2,000 years, a little around that age, whereas the CSM model produces ages that are well above 3,600 years in the deep North Pacific. So the model is much too weakly ventilated in the North Pacific. All right, so this is where the sediment-core locations are from the compilation of Skinner and Emma Freeman. And so you can see where they are. They're mostly around the coast, but there's quite a few in different basins. So I've used those locations and went into the model and picked off the measurements at the surface and at the deep at the same place where the sediment-core data are to make a pseudo data. All right, so then I use those data and I calibrate those weights in the tracer transport operators using some optimization to find those that best fit the model. So this is the benthic planktonic age fitted, my fitted model using the coarse resolution model. And this is the age sampled in the CSM model, which is my quote-unquote LGM test case. And you can see that after fitting it, the model does a reasonable job. There's a fairly good one-to-one trend for the model case between the fitted and the observed one. So once we've done this, then we have a tracer transport operator that we can then use to make inferences about things that are not directly measurable. So this is what the LGM CSM-POP field I showed you before, and this is the reconstructed one using these tracer transport models. And the pictures looks reasonably good in terms of the large-scale patterns. So we had a few sparse measurements, and from the sparse measurements and the built-in information from the suite of tracer transport operators, we can get a reasonable fit to the radiocarbon. And so in this case, the globally averaged age of the CSM-POP is about maybe 1930 some years, and the reconstructed one is off by maybe 100 years. So it kind of gives you an idea of how accurately we might be able to do this with real data. All right, then I tried it with real data, and unfortunately, in the real data, the fit is not nearly as good. So that could mean several things. Could mean there's more noise in the data, but it could also mean that the suite of operators I have from my coarse resolution model, they don't span enough possible circulation configurations to actually fit the data. So before I hope to get some more serious results, I want to run more versions of the model with different forcings so that we might be able to get a better fit. In any event, we plow ahead and calculate the pictures. So this is what the best fit from the actual sediment-core data, the BP sediment-core data, showing the mean age, or the age. This is zonal average in the Pacific, the only one I'm going to show. And this is the GLODAP again. Same picture from last time, except now the scale is more reasonable for the data. So we see in the modern ocean, the radiocarbon ages are maybe around 2,200 years in the deep North Pacific. From the reconstruction, of course, there's some large uncertainty. You saw the scatter from before. We get older at the bottom in the Pacific, so there's kind of more stratified in terms of age and older water overall. And and it also suggests, if I'm going to believe the results, but they're very preliminary, is that glacial ocean would be around 300 years older than the modern ocean. 300 on average. This is the average. So in the deep Pacific, it's actually quite a bit older than the modern. But once you've globally averaged, then the numbers are much, about 300 years. All right, so I'm already ready for my summary. So the ocean circulation in this estimation method is represented as a linear combination of tracer transport operators from a suite of OGCM results. And then we use the Bayesian inverse method to reconstruct the linear combination of these transport operators to fit the data. And the beauty, or the nice thing about this is after you've gotten this posterior distribution, you can then go back and randomly sample these weights that we've got the posterior PDF for, and then you can explore the sensitivity, or you can get some error bars on your inferences that you would make with this tracer transport method. So I haven't done this yet, but this is possible to do this. And you might find out that some things like the global average age may be very well estimated with a small number, but then if you try to zoom down into particular regions of the ocean, then you'll be able to find bigger or smaller error bars. So it's useful to be able to do this, to get the error bars. When I tested the method with simulated data, the method worked very well. However, it didn't do quite so well in the real data, and the reasons for this are still uncertain, but presumably it's because the GCM I have was a GCM. I was comparing two GCMs which may have a kind of a limited number of states that they can explore, and the real ocean maybe is more variable. In any event, I'm going to explore more dynamical models to try to redo this fit. And maybe a very preliminary results which suggest that the global average LGM was maybe 300 years older on average. This is very uncertain. And that's all I have. Thank you.
So, thank you. We have time for a short question. Yes, please come to the microphone.
I have a question about how you do the surface boundary condition for C14 in terms of if you have significant change in the sea ice cover, you might change the way it equilibrates with the atmosphere.
Right, so the question was how to do the sea ice cover. That could be taken into account. I had in one of my parameters was this restriction on the air-sea gas exchange. So at the risk of increasing the uncertainty, the surface ocean might be tiled in different regions and then allow, as part of the inference, to change the efficiency of air-sea gas exchange to try to reconstruct that. Just as a word of caution though, when I tried to redo the POP recalibration and I had it completely free to change the surface air-sea gas exchange, I was able to fit the data very well also, but with this very, very small air-sea gas exchange. So the ages were, you know, in the tens of thousands of years, but the BP gradient fit the data very well. So it'll be very useful to have some surface planktonic radiocarbon ages so that we can try to constrain that bit of it. Thanks.
All right, thank you.